Python Sets, Intermediate Beginner Guide. In this lesson, we will dive into sets in Python. Sets let you store unique items. They are great for removing duplicates and handling collections where order does not matter. Let us explore how to use them, important operations, and practical benefits. Running the cell now. Let us start by turning off any warnings that might pop up. We will then learn how to create a simple set in Python. We need to import the warnings module. It will help prevent extra messages in our output. Import numpy as np. We set the random seed to 42 for reproducibility. Using filter warnings makes sure our notebook stays clean. A set is a collection that stores only unique items. Here is an example set containing the numbers 1 through 5. We create my_set using curly braces and several numbers. When we print my_set, we see the set's contents. The order might be different than what we typed, since sets are unordered. Running the cell now. This output shows the creation of a set containing the unique integers 1 through 5. Notice how the set elements are displayed in curly braces, emphasizing that sets store unordered, unique items. This example highlights the simplicity of defining a set with distinct values, the foundation for exploring set operations. Why use sets? Sets are perfect when you only want unique items. They are fast for checking membership. Great for data cleaning, like removing duplicate entries from a list. Running the cell now. Let us see how sets help clean up a list with duplicate items. Sets are helpful when you have duplicates you do not want. Here, the list numbers contain several repeated elements. We create a set from the list. The set keeps only unique values. Printing unique numbers shows how duplicates are automatically removed. Running the cell now. This output shows a set containing only the unique numbers from the original list, demonstrating how sets automatically remove duplicates. Notice how the repeated values like 2, 4, and 5 appear just once, highlighting the set's efficiency for data cleaning when you need distinct items. This reinforces the lesson's point about using sets to quickly eliminate duplicates and streamline data. Let us create an empty set and note an important difference. This line is a comment explaining that we are creating an empty set. Here we create an empty set by calling the set function. This line prints the empty set we just created. This comment explains that using empty curly braces creates a dictionary, not a set. Running the cell now. This output shows an empty set displayed as set, confirming that empty_set was correctly initialized with the set function. Notice that using would create an empty dictionary instead, so this distinction is important when you want to start with an empty set for tasks like removing duplicates or checking membership efficiently. Let us check if certain items exist in our set. Sets are fast at checking if a value is inside. We create a set named fruits with apple, banana, and cherry. This line checks if banana is in the set. It will return true. We check for orange too. That one returns false since orange is not included. Running the cell now. This output shows how sets efficiently check membership. Banana returns true because it's in the set, while orange returns false since it's not. Notice how this quick lookup highlights set's strength in verifying the presence of unique items, which is key for data cleaning and avoiding duplicates. Syntax recap. Curly braces for sets with items 1, 2, 3 in braces means a set. Use set with parentheses to make an empty set. Duplicates are removed. Sets are unordered. Their contents may show up in any order each time. Running the cell now. Sets do not support indexing the way lists do. Here is how you can see what is inside instead. Because sets have no order, you cannot use indexes to get an item. Let us make a set of color names. If you try to use an index, Python will complain. We will skip running that part here. Instead, you can use a for loop to go through all items in the set. This prints each color in the set, in any order. Running the cell now. This output shows the items in the colors set printed one by one, highlighting that sets are unordered collections. You see the colors in no guaranteed order. Since sets don't support indexing, the commented out print, colors 0, would cause an error, reinforcing that you must loop through sets to access their elements. This example connects to the lesson by demonstrating how to properly work with sets using iteration rather than indexing. Let us see how to add and remove items from a set. Notice what happens when we use remove. Adding items is easy using the add method. We create pets as a set with cat and dog. Here we add hamster. The set now contains 3 pets. Printing shows that hamster has joined. Now, we remove dog from the set. That item disappears. The printed result shows the new set. Trying to remove something not present will cause an error with remove. Running the cell now. The output shows how items are added and removed from a set. First, hamster is added to the original set, cat, dog, resulting in 3 items. Then, dog is removed, leaving cat, hamster. This demonstrates that sets are mutable and unordered collections with unique elements, key for managing dynamic groups of items. There is a safer way to remove items where missing values do not cause errors. Use discard if you are not sure the item is present. We make pets 2 with cat and dog. Trying to discard parrot, which is not there, will not cause any error. Printing confirms pets 2 is unchanged. Running the cell now. The output, cat, dog, shows that using discard to remove an item not in the set doesn't cause an error, it simply leaves the set unchanged. Notice the order may vary, reinforcing that sets are unordered collections. This highlights the safety of discard compared to remove. Set methods: add, remove, discard, and more. Add adds a value to the set. Remove takes one out, but you get an error if it was not already in the set. Discard is safer and will not complain if the item was not present. Pop removes a random value from the set. Clear erases all items, leaving an empty set. Running the cell now. Let us see pop in action on a set. Pop removes and returns a random element. Here we make a set from a few numbers. We call pop and store the result in item. Printing shows what value came out. We also print the new state of the set, which has one fewer value. Running the cell now. The output shows that pop removed the element 40 from the set, which is then reflected in the updated set missing that number. Notice that since sets are unordered, pop removes a seemingly random item, highlighting why it's not ideal when you need control over which element to remove. This demonstrates the unpredictable but effective removal behavior of pop used in set manipulation. If you want to empty a set, use the clear method. Clear is an easy way to delete all items at once. We start with a_set containing a few numbers. After using clear, our set is now empty. Printing will show set, indicating it has no items. Running the cell now. Here we see the output set, indicating the set is now empty after using the clear method. This confirms that clear effectively removes all elements at once, resetting the set to an empty state. Understanding this helps us manage sets by quickly emptying them without needing to remove items individually. Set operations: union, intersection, difference, symmetric difference. Union combines everything from both sets. Intersection finds what is shared. Difference gives items that are only in the first set. Symmetric difference means values found in only one set but not both. Running the cell now. Let us put set math into practice with some examples. We create set A with the numbers 1, 2, 3, and 4. We create set B with the numbers 3, 4, 5, and 6. Print the contents of set A to see its elements. Print the contents of set B to see its elements. Print the union of A and B, which combines all unique elements from both sets. Print the intersection of A and B, showing elements common to both sets. Print the difference between A and B, which shows elements in A but not in B. Print the symmetric difference of A and B, which shows elements in either set but not in both. Running the cell now. This output clearly shows how set operations work. The union combines all unique elements from both sets, while the intersection highlights only the shared elements, 3, 4. Notice the difference, A, B, returns items exclusive to A, 1, 2, and the symmetric difference includes elements unique to each set, excluding the intersection. This reinforces the concept of how these operations help compare and manipulate collections of data efficiently. Let us see this using set methods with words for variety. You can perform set operations using methods like union, intersection, difference, and symmetric underscore difference. Here we define set 1 with elements A, B, and C. Here we define set 2 with elements B, C, and D. We create UD as the union of set 1 and set 2, combining all unique elements. We create INR as the intersection of set 1 and set 2, containing only common elements. We create D as the difference of set 1 and set 2, elements in set 1 not in set 2. We create S as the symmetric difference of set 1 and set 2, elements in either set but not both. Print the union result labeled as a union. Print the intersection result labeled as intersection. Print the difference result labeled as a difference. Print the symmetric difference result labeled as symmetric difference. Running the cell now. This output shows the results of set operations on two sets, set 1 and set 2. Notice the union combines all unique elements from both sets, the intersection captures only the common elements B and C, the difference highlights items unique to set 1, A, and the symmetric difference lists elements in either set but not both, A and D. This demonstrates how these methods help compare and combine sets based on their shared and distinct values. Sets also help compare if one set is contained within another. Let us check for subset and superset relationships. Define main_set as the set containing 1, 2, 3, 4, 5. Define sub_set as the set containing 2, 3. Print whether sub_set is a subset of main_set. Print whether main_set is a superset of sub_set. Running the cell now. Here, the output shows true for both isubset and isuperset, confirming that sub_set is fully contained within main_set, and main_set includes all elements of sub_set. This demonstrates how to check subset and superset relationships, crucial for understanding hierarchical set connections beyond just combining or comparing elements. Let us clean up a list of names containing duplicates. In real life, names or items might repeat by mistake. Turning the list into a set drops repeats. Then, we turn the set back to a list to get a tidy version. Print shows the list with only one of each name. Running the cell now. Here, the code converts a list with duplicate names into a set to remove duplicates, then back to a list. Notice the output contains only unique names, demonstrating how sets efficiently filter out repeated items. This aligns with the lesson's intent to show practical uses of sets in data cleaning and uniqueness. Sets are a lot faster for membership checks than lists are. How does checking if an item is in a set compare to checking if it is in a list? We create a large list of numbers from 0 to 99,999. We convert that list into a set for faster membership testing. We import the time module to measure how long operations take. We record the current time before checking if 5,000 is in the list. We check whether 5,000 is in big_list and calculate the elapsed time. We record the current time before checking if 5,000 is in the set. We check whether 5,000 is in big_set and calculate the elapsed time. We print the time it took to check membership in the list. We print the time it took to check membership in the set. Running the cell now. Here, we're comparing membership check speeds for a list versus a set with 100,000 elements. Although both times show as 0 seconds due to very fast operations, the intent is to highlight that sets typically have much faster membership checks because of their hash-based structure. This supports why sets are preferred for operations like union and intersection when performance matters. Real-world example, survey results. Suppose you are working with survey responses and want to see how many unique people entered. Running the cell now. Let us count unique survey participants using a set. In this example, some people filled out the survey more than once. By creating a set from responses, we get each person only one time. Printing shows who replied. We also print out the total count with len. Running the cell now. This output shows the unique survey respondents extracted from a list with duplicate entries. The use of a set helps identify distinct names, and the length function counts how many unique people answered, which is key for understanding the true sample size in survey data. This step ensures accurate analysis by eliminating duplicates. Practical mini-project, set operations with words. Suppose you want to compare words found in 2 sentences. Running the cell now. Let us compare 2 sentences and see word differences with set operations. Our first sentence repeats words, which is common in writing. The second adds some new words. Turning each into a set of words automatically removes repeats. Now, we use set operations. Intersection shows the words used in both sentences. Difference gives words found only in the first sentence. Symmetric difference finds the words present in just one sentence, not both. Running the cell now. This output shows the results of set operations comparing unique words in 2 sentences. Notice that the intersection and identifies words common to both sentences, while the difference dash shows there are no words unique to the first sentence. The symmetric difference caret highlights words that appear in only one of the sentences, emphasizing how set operations can reveal similarities and differences in textual data. Let us practice making a set from what you type. This is a comment describing the challenge to create a set from user input. We ask the user to enter items separated by commas and store the input as a string. We split the input string by commas and strip extra spaces to create a clean list of items. We convert the list of items into a set to keep only unique elements. We print the set showing the unique items entered by the user. Running the cell now. This output shows the unique words the user entered, displayed as a set. Notice that duplicates are removed and the order may differ, which demonstrates how sets help identify distinct items from a list. This aligns with the lesson's goal of using sets to compare and handle words efficiently. Common mistakes with sets. Remember that sets do not keep order of items. Using creates an empty dictionary, not an empty set. Only items that cannot change, like numbers or strings, can be put in a set. Running the cell now. Let us look at why only certain types of items can go in a set. Sets require each value to be immutable. That means you cannot use lists or other sets as items. We create my_set as empty. Trying to add a list would create an error, so we do not run it here. Adding a tuple works fine because tuples are immutable. Printing shows the tuple in the set with no issues. Running the cell now. Notice that the output contains a tuple, 1, 2, 3, inside the set, emphasizing that only immutable items like tuples can be added to sets. This code demonstrates the key lesson that mutable types such as lists cannot be added, preventing the type error shown in the commented line. Let us see how many unique words are in something you write. Type in a sentence. We will split it and remove repeats by using a set. We turn everything to lowercase so that same words with different letters count as one. Now the set words has all unique words present. We print out a count using len to see how many you used. Running the cell now. This output shows the number of unique words in the user's sentence, illustrating how converting a list of words to a set automatically removes duplicates. Notice the use of set to create an unordered collection of unique, immutable items, which directly helps count distinct words regardless of their original order or repetition in the input text. Let us use sets to quickly find overlaps and differences in two groups. This comment explains that sets can be used to quickly compare two groups of data. Here, class_A is defined as a set containing the names Amy, Ben, and Kara. Similarly, class_B is defined as another set with names Ben, Derek, and Emma. This line finds the common elements intersection between class_A and class_B. This line finds the elements that are in class_A but not in class_B. This line finds the elements that are in class_B but not in class_A. This prints the members who are in both class_A and class_B. This prints the members who are only in class_A and not in class_B. This prints the members who are only in class_B and not in class_A. Running the cell now. Here, the output shows how sets can quickly identify common and unique elements between two groups, in this case, students in two classes. Notice that Ben appears in both classes, while the Kara and Amy's are only in class A, and Emma's and Derek are only in class B, demonstrating set intersection and difference operations. This highlights the power of sets for comparing groups without worrying about order. Challenge: unique characters in a name. Type your name and see how many unique letters it has. Running the cell now. Let us count the unique letters in any name. When you type your name, we turn it into lowercase and remove spaces so only letters remain. Making a set removes repeated letters. Printing shows all the individual letters. We also count how many different letters are in your name. Running the cell now. Here, the code takes your name, removes any spaces, and converts all letters to lowercase to ensure uniformity. The output shows the unique letters found in the name and counts them, helping you see exactly how many different characters you used. This demonstrates how sets can identify distinct elements in a string, which is the goal of this challenge. Best practices when using sets. Use sets when you only care about unique items. It is best not to rely on the order of things in a set. Use set operations to write clean, understandable code. Running the cell now. Let us revisit how quickly sets clean up repeating items. We start by stating the goal, removing duplicates from a list. Here is our initial list, which contains some repeated items. We convert the list to a set to eliminate duplicates, then back to a list. Finally, we print the list to show the duplicates have been removed. Running the cell now. This output shows how converting a list to a set removes duplicates, leaving only unique items like pencil, pen, ruler, and a book. Notice that the order of items is not preserved, highlighting the lesson's point about not relying on order when using sets. This method is a clear and efficient way to get unique elements from a list. Let us tie in variables with sets for a practical example. This line introduces a fun example that uses variables and sets together. We create a list named first_names containing 3 first names. We create a list named last_names with 4 last names, including duplicates. We convert the last_names list into a set named unique_last to keep only unique names. We print the unique last names to show which ones are not repeated. Running the cell now. This output shows the unique last names extracted from the list, demonstrating how converting a list to a set removes duplicates automatically. Notice that the order of items in the set is not guaranteed, but what matters here is that only distinct values remain, which aligns with the lesson's advice to use sets for uniqueness without relying on order. This makes the code clearer and more efficient when we only care about unique elements. Summary: what have we learned? Sets store unique, unordered items. They are fast for membership checks. Use set operations for clean solutions. Remember, sets require immutable values. Running the cell now. Want more practice? Try converting data to sets in your own projects. Explore set operations with real-world lists. For more tutorials, subscribe to our channel and watch the next video. Running the cell now.